Hi, my name is Joshua Saxe, and today with Younghoo Lee, I'll be presenting Detecting Handcrafted Social Engineering Emails with a Bleeding Edge Neural Language Model. A bit about us before getting into the talk. I'm Chief Scientist at Sophos. Sophos is a security products and services company. We have a whole range of security products ranging from firewalls to mobile security to email security to endpoint security. And the team that I manage, Sophos AI, is the AI shop inside of Sophos. We research and develop the company's machine learning technology, and then we're also responsible for operationalizing that technology in service of defending about 100 million endpoints. Younghoo Lee is one of the star researchers on my team. He's almost completely solely responsible for the machine learning subsystem that protect our Android customers. At least for he's responsible for the R&D part of that work. He's also the principal author of the work presented today. I'm presenting in a supporting role here. I'll mostly just be setting the stage for the original work that Younghoo is going to describe. So, the problem we're solving. Most generally, we're working on the problem of detecting phishing emails. More specifically, we're working on detecting business email compromise phishing emails and targeted phishing emails. So to understand what this is, it's useful to say what it's not. We're not focused on detecting mass campaigns where detection reduces to a near duplicate detection problem because attackers are just sending out millions of copies of basically the same phishing email. Detecting those types of emails turns out to be a side effect of our focus, but our real focus is on detecting new custom-authored bespoke phishing emails that are based on research on a target. And this diagram does a good job of getting across the kind of workflow we're looking at stopping. In this workflow, cyber criminals and attackers identify targets through open source research, usually on the web. Then they establish contact with those targets. In step two, we call this grooming. In this case, they put out a lure, an initial email, usually, or sometimes an initial text message, and then build trust and authenticity around some identity that they're impersonating with the mark. In step three, they cash out the trust that they've built with their targets and make an ask of those targets. Oftentimes, that ask will be around wiring money or sending credentials, and then in step four, they actually receive money or receive the credentials. So within targeted phishing, business email compromise, which is focused on stealing money from businesses and other organizations, has been a growing trend. So as you can see here, in July 2016, a few $1 billion were stolen, according to the FBI, through business email compromise attacks. And these are targeted phishing attacks that extort money from organizations. In May 2017, that number had grown to almost $6 billion, and in 2018, that number had grown to more than $12 billion. I don't have data for the last 2 years, but I see no reason to believe that that this trend has attenuated. I think it's likely it's continued on a similar trajectory. This is a big problem. We see this in Sophos' customer base, which is a pretty large sample. We also hear about it from other folks in the cybersecurity space. And so we're very focused on it because it's affecting people. And it's not just affecting large organizations. You can see on the axis on the right, that something like 80,000 organizations had been hit by July 2018 by these attacks. So there are lots of small and mid-sized organizations getting hit, and oftentimes the financial damage can be in the hundreds of thousands of dollars and really impact people's lives when these attacks happened. So again, just to reiterate, we're focused on primarily these business email compromise use cases, but also more generally targeted phishing, in which a lot of manual labor goes into the phishing process on the criminal actor side. And I think it almost goes without saying, but we're focused on step 2 and 3 of these criminal actors' workflow, the steps that are mediated over email. So we see lots of malicious emails exchanged in the grooming step, and then we also see, obviously, a malicious email transmitted in the exchange of information step, where the attacker makes the ask of the target, usually employee. and this is just because we're focused on email as our signal, and that's the scope of the work that I'll be talking about today. Just to flesh this out a little bit, here's an example phishing email sent in the later sort of epochs of the grooming stage of an attacker's workflow. Here, the attacker has established themselves as an impersonated chancellor of UC Berkeley. They are emailing an employee at UC Berkeley asking if they're available, looking to exchange messages with them, probably about to make an ask around a money transfer. Now, I think it's important to highlight why phishing detection is hard, and why in particular detecting new, previously unseen phishing emails written as part of a manual phishing campaign like what I've just described is hard. And what this boils down to, I think, is that classical natural language processing problems are hard. It's hard to get computers to understand language in any meaningful way and reason about language in any meaningful way. And detecting phishing emails really boils down to building models that have some level of understanding of language. So to understand why algorithmically it's hard to make sense of language, let's look at a few classical natural language processing problems. So one of those is coreference resolution. To get a sense of what this problem means, consider the following sentence. I went to the store for some milk and based on the price decided to buy it. Now, from a grammatical perspective, it could refer to the store or to the milk, right? It's possible that I went to the store for some milk and based on the price of the store I decided to buy it, but it's more likely that I bought the milk. As humans, in solving this coreference resolution problem, so resolving what it refers to, we have to plumb the depths of a number of complex mental models, right? We need to deploy our syntactical model of the English language, our semantic model of the English language, and our model of the world in which a person is more likely to have bought milk at the store than have bought the store itself, and that's how we solve this problem. Hopefully it's clear that it's hard to get algorithms to do that. But to detect phishing emails, we really need to understand language, and this is a problem that's constituent of the problem of understanding language. Word polysemy is also a classic problem in algorithmic understanding of language. So a sentence like he drank a lot and was quite the rake. Grammatically, it's valid to interpret this sentence as meaning that he drank a lot and was quite the garden tool used to rake leaves off your lawn. That's clearly not that's not the sense in which the word rake is being used. The word rake is being used in the sense of a drunk, semi-criminal, sort of dissolute individual here. But it takes a pretty deep exercise of a human being's mental models to arrive at the sense in which this word was used, and not easy to reproduce in the form of an automated agent, either machine learning or based on regexes and rules. Sentiment detection is another hard problem in natural language processing. So consider the sentence, I'm not angry at all. No, of course. Why would I be angry that you spent our life savings on your mistress? So clearly the speaker is angry here, and they're being sarcastic. Detecting that they're angry and sarcastic is not trivial and requires that we understand not only the syntactic structure of the sentence, but also the semantics of the sentence, and requires that we have the reflex that this person is probably angry if their interlocutor spent their life savings on their mistress. Okay, so to solve phishing means that we need algorithms that can make sense of language. Making sense of language is hard, as these three problems demonstrate. So a good solution to the phishing problem would model as intermediate steps to detecting that a email is a phishing email. At some level, be able to solve these problems, and somewhere in the depths of its intermediate representation of the language that it's looking at. The other challenge we have, obviously, in any cybersecurity problem, or at least any detection context in cybersecurity, is that we have adversaries who'd like to bypass our detection, and that's also worth considering. So these are all reasons why the problem that we're presenting here is a hard one. We haven't solved it completely. Deserves attention from our community. Now, the approach that we're using to attack the phishing problem is based in neural networks and deep learning, and a specific advance that happened in the last few years known as transformers. So transformers, or more specifically transformer blocks, are a new kind of construct in neural networks, much like convolutions were new, I think, as of the 90s or late 80s, and backpropagation was a new idea in neural networks, I think, starting in the 80s. Transformers are a new idea that's come out in recent years, and they help model language with a depth and fidelity that seems to be genuinely new and represent a step function in our ability to model language. So they're very exciting. The big idea behind the work that we're presenting today is that we're taking transformers and applying them to a cybersecurity problem, which we haven't seen much of before. So I'm going to talk a bit about what transformers are. A detailed discussion of how they work is beyond the scope of this talk, but I'm going to give some intuition, and then I'll pass the mic metaphorically over to Younghoo, who will present on how we're using transformers. Okay, so here's an example which I think helps to illustrate some ways in which transformers represent a real breakthrough in machine comprehension of language. So in this example, and I expect some of you have seen this because this sort of went viral last year, a researcher wrote a prompt. This prompt is given at the top here in a shocking finding, that paragraph. And then a transformer model just sort of took it from there and wrote a story based on that prompt. And I think when you see the story that the machine wrote, you'll see that it betrays a understanding of the syntax and semantics of language that's quite striking. So I think it's worth reading this out loud. The human-written prompt reads, "In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English." And now again, the challenge to the model is to see if it can pick up where the human left off and write something coherent. And if it can, that reflects something around its ability to solve problems like the fundamental problems I described earlier. So the neural network continues. The scientists named the population after their distinctive horn, Ovid's unicorn. These four-horned, silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. Dr. Jorge Perez, an evolutionary biologist from the University of La Paz, and several companions were exploring the Andes Mountains when they found a small valley with no other animals or humans. Perez noticed that the valley had what appeared to be a natural fountain, surrounded by 2 peaks of rock and silver snow. Perez and the others then ventured further into the valley. By the time we reached the top of one peak, the water looked blue with some crystals on top, said Perez. And the essay continues. But what interested Younghoo and I in seeing examples of what transformers can do like this is that it seems that the transformers have, examples like these suggest that the transformers have understood the syntax and semantics of the English language to some degree, and which begs the question, could the representations that the transformers learn in their parameter structure be useful in detecting phishing emails, since these transformer models seem to have distilled knowledge of how language works and what it means within their parameter settings. Okay, so this is one example of sort of impressive example of what transformers can do that beg the question of whether or not they could be applied usefully to phishing, and we'll show results from our experiments later in Younghoo's section. Here's another example of just how sort of marvelous transformer models are with respect to how much more sophisticated they seem to be. So here a researcher typed into this box a description of some HTML that he would like the transformer model to generate. He writes, "A button with the color of Donald Trump's hair," and then the model actually writes as a text completion some HTML and CSS. It seems to understand that Donald Trump has yellow hair, and it makes a button, and it writes valid HTML and CSS, which is, I think, just impressive in the absolute sense, but also for folks who've been in the NLP space for a while, it's impressive relatively. 5-10 years ago, if you would have shown somebody that we could do this in 2020, I think they would have been a bit incredulous. This is a big step forward. Applications like these represent a big step forward in natural language processing, and they're due again to this new idea called transformer block. That's the key building block out of which models like this model, which is called GPT-3. It's from OpenAI, which is an AI research lab, are based. Okay. So moving on. So I want to go back a little bit in the history of NLP to just as a way of describing how transformers are new and different. So I assume a substantial chunk of our audience today has studied basic machine learning on text, and typically in like a machine learning 101 course, you learn about the bag of words model and about discrete state Markov models of language. And I want to talk about these representations as a way of talking about how limited those representations were, and then I'll talk about how transformers break us free of some of those limitations. So a bag of words model of a document is a way of representing a document numerically for the purposes of machine learning, in which we just count up how many times each word in that document appeared, and then we create a matrix out of all the documents we have and all the words in all those documents. And the entries in those matrix are just word counts. So in the case on the left over here, the column vectors in our matrix are documents, and they get one dimension per word in our vocabulary, and they get counts of how many times words appeared in that vocabulary in the entries of that particular vector. And hopefully it's intuitive that, once you've represented your documents in a vocabulary space in this way, you can compare documents by taking some distance measure between pairs of documents. You can also train machine learning models on your document corpus to, say, classify news articles as about sports or politics. But what you've done in the first step of these models is drop out sequence information. So you've forgotten about which words come in which order in the document, and you've just represented your document as a bag of words, which is a useful simplifying assumption, and it's one that we still use today in some of the modeling we do in my research group at Sophos. But it throws out a ton of information that transformers and more modern models don't throw out. In the model on the right we have a discrete state Markov model of language. Here each word is a state, and the concept of language given by the model is kind of a choose your own adventure story in which the next word in an utterance depends only on the current word, and you're just sort of drawing from a probability distribution and moving through this graph to generate language. You could never have generated anything close to that unicorn story using a Markov model, and yet as recently as the last 5-10 years, there's lots of papers coming out around like using hidden Markov models to parse sentences and that kind of thing. These are still useful models, but we've gone far beyond the simplifying assumptions in these original sort of simplified models of the world in NLP from the past few decades. So let's contrast transformers now, and I'll get into more details about how transformers work in a second. But let's contrast transformers with these earlier natural language processing approaches. So pre-transformer, most machine learning approaches didn't consider words in context. Many approaches made the simplifying bag of words assumptions as kind of a first step in the modeling process, and then ran term vectors through models like topic models or logistic regression or support vector machines. Most models didn't model kind of like co-reference relationships between words, or sort of which words pertain to which other words in a sentence, and I'll talk about what that means later, but transformers do sort of solve that problem. Most approaches didn't. Most approaches operated on either words or characters. transformers have, typically the way people use transformers, we use well-chosen chunks of words, which allows us to model misspellings and this kind of thing. So there's been an improvement there in the current generation of natural language processing models. And older approaches tended not to use neural network technology. That's changed a lot in the last 10 years. But transformers leverage some of the best ideas that have come out of the neural network revolution that's been ongoing since around 2012. So transformers kind of kick apart a number of log jams in natural language modeling. They give words contextual representations. They model attention, like the relationship between words in a document. They use these smart partial word representations that allow for misspellings and just the Tower of Babel of vernaculars that appear like under the banner of, say, the English language on the internet. And they take advantage of ideas like residual connections and modern optimizers and many of the really good ideas that have come out of the neural network revolution. So these are all reasons why we wanted to test their applicability to phishing detection. Okay, so if you want to get into detail about how transformers work, I'd recommend this blog post by Jay Alamar. It's where I cribbed this screenshot here. I'm not going to get into the details of the series of matrix multiplications that comprise and summations and various linear algebra and operations that comprise a transformer block. I just want to give a little bit of intuition here before passing the mic over to Younghoo. The basic idea behind a transformer block, which is kind of a Lego block out of which you build a transformer-based neural network, is we're taking in a sequence of words. This diagram shows a very simple example where we just take in a sequence of 2 words. Typically, we take in a larger window, like 512 words. We pass them into the block. And the way they get passed in is as not just as entries in a term vector matrix, but actually as vectors themselves. So the words get a vector representation. These are known as embeddings. We pass them both into the transformer network. The first thing that the transformer network does to our input word sequence is model the attention relationships between the words. So basically, I mean, in a 2-word case is a little bit harder to describe here, but basically if you had like a sequence of like 15 words, for every word, the attention mechanism would compute how much that word pertains to the other 14 words in the sentence. And you'll see how that has a relationship with like the co-reference resolution problem I talked about earlier. But it's just intuitive that there's a graph of words, word relationships in a sentence, and self-attention kind of models that in terms of which subjects pertain to which objects, which pronouns pertain to which people, etc. There's an addition and normalization step that happens when we've sort of run this self-attention process a number of times. Typically, we don't just do self-attention once. We have a number of what are called heads, and when we run attention a number of times. We combine all that together, we do some nonlinear transformation on it, and then we wind up with a new embedding of our original sequence of the same dimensionality as this original embedding, except that now thinking is encoded in this new representation in the context in which it appears, in the context of machines. Machines is encoded in the context of thinking. And then typically we stack these transformer blocks, so we have another transformer block that then sort of refines the representation, and we keep going. Younghoo will show that we use a number of transformer blocks in our phishing detection work in a few minutes. So here's some intuition as to what comes out of the attention mechanism in a typical transformer. So here's what a transformer block has decided it sort of relates to in an input sentence. So here we have the input sentence: the animal didn't cross the street because it was too tired. And the strongest attentional relationship here goes to the animal, which is interesting because one could ask whether or not it refers to the street or the animal here. One can interpret the weight of the connection to the animal, meaning that the transformer block has decided, in air quotes, that it pertains to the animal, which is really interesting. So hopefully you get some intuition as to how powerful this attentional representation is and how important it is in machine learning models gaining some what we might call understanding over the language that they're analyzing. Okay, so I want to put the intuition together around how transformers pertain to the work that Younghoo and I are presenting today. So basically, what we're going to do in our phishing model is embed an email as a sequence of embedded character sequence vectors, and then we're going to run that through a series of transformer blocks, like what I just showed, that are going to create a very refined attentional representation of the word sequences, and then produce these contextual embeddings that get at the meaning of the words in the context in which they appear. And then finally, our network is going to solve a classification task, say whether or not the email is a phishing email or not. How all that magic works, how the network gets trained, which there's some tricks there that are really cool, I'll leave to Younghoo, and hope a lot of this makes sense, and happy to take questions about my piece of this presentation later at the end of the talk.
Thank you, Joshi. Let me continue the second part of our talk. The second part will include our design decisions for chatbot and performance result. Chatbot is the name of our email model, context-aware tiny bot. The model size is tiny, but it is mighty bot. Modern NLP models all have a nice and friendly name. For example, Elmo was introduced 2018. The model used bidirectional LSTMs to generate contextualized word embeddings. And then, same year later, Google researchers introduced BOT and achieved the state-of-art performance in many English understanding problems. Next year, 2019, Baidu researchers introduced the Oni, and the model achieved another state-of-art performance in many Chinese language understanding problems. They are all popular characters from Sesame Street. This year, 2020, we introduced Catbot to tackle email security problems. Transformer-based NLP models are powerful, but they are complex and heavy. And it is challenging to deploy heavy models for real-time applications. So our first design goal is to convert the heavy model into lightweight model, so we can reduce number of parameters and then we can improve inference speed. We downsize a baseline model called DistillBot, which has 6 transformer blocks. We take half of transformer blocks from pre-trained model and then replace missing transformers with simple adapters. For example here, we take transformer 135 and then we added 2 adapters. Also, we can take other number of transformer blocks. This approach allows us to simply significantly reduce number of parameters. The second goal is to improve the model performance by combining additional input. Standard NLP models only accept text data as input. However, we can extract additional features from email headers and we can use the additional input to our model. So the text input will be the input to the embedding, and then we can add additional input to the classification adder, and we added additional dense layers in the classification to combine the input from transformer block and another header-related input. With the additional input, we improved our model's performance further. Let me talk about the details of our adapters. We inserted 2 adapters here, and each adapter has quite a simple architecture. Each adapter will have 2 dense layers, and there's one nonlinear activation unit in between, and we have a skip connection. The dimensionality of the dense unit are same as the output of transformer blocks. And the 2 dense layers are initialized with near zero values. So as initially, the adapters will act as identity blocks, but however, they will gradually change the data from the lower transformer block to upper transformer block, and to minimize classification loss. We also modified the standard fine-tuning method by using a partial fine-tuning method. Standard fine-tuning involves updating all parameters jointly. However, partial fine-tuning, we only update upper blocks, but we fix lower blocks. For example, here, the lower blocks embedding the transformer 1 and 3 are fixed, but we update adapter 1 and 2 and transformer 5 and classification header. This approach was to minimize forgetting problems of learned presentations from low transformer blocks. As mentioned earlier, we have 2 sets of features, one from text data and another one from email headers. We can use multiple email header filters, for example, from 2 CC reply filters to extract additional context information. And we consider the subject and the text as context input. The first set of features are from email text, content features. We extract text data from subject and plain text body. If only HTML content is available, then we can also extract plain text from HTML data using a HTML parser. For example, this one is a simple HTML hyperlink, but we only extract visible text visit bank site as output. And then from the extract text, we remove less informative characters. We remove digit and punctuation characters. The second example, there are many hyphens, but the hyphens will be removed in this step. Otherwise, each hyphen will be individual token. Finally, we select 120 tokens as input to the transformer blocks. We use a subword tokenizer called word piece. The word piece tokenizer can overcome some of the limitations from character level or word level tokens. Character level tokens are too fine-grained, so it is hard to recognize word boundaries and the meaning of words. And word level tokens often have out-of-vocabulary problems. The subword tokenizer can split complex or uncommon words into sub-tokens. For example, catbot can be divided into simple cat and bot, and double hash is a indicate per subword. Similarly, sophos can be divided into three tokens: SO, PH, and OS. The subword tokenize reduced number of unknown tokens in our email data. With the selected tokens, the tokens will be the input to the embedding layer, and then we have three transformer blocks, and each transformer block has 12 multi-head attention layers, and each individual attention layer learns contextual relationship between tokens. And the right diagram shows attention weight between tokens. The transfer token has multiple attention weight for other tokens. In our email data, we have many non-English emails, and also non-English emails can include English words. Also, English emails can include non-English words. The non-English emails account for 25% of our total benign and malicious emails. So we needed to support multilingual model which can recognize different languages. How we can support multilingual emails? The solution is bot comes with two versions, English and multilingual bot. The English version was pre-trained with large English text data sets including Wikipedia and has 30,000 English tokens. The multilingual version was pre-trained with large text data sets from more than 100 languages, and this version has 4 times large vocabulary size, which is 120 tokens, which will cover many Unicode characters and Unicode words. So we fine-tuned a multilingual bot for our multilingual emails. The second set of results from email headers. We can extract multiple indicators from email header builders. For example, the first one, we check whether the emails are from internal or external. We can compare the domain of recipient and the sender. For example, here, the domain name is a similar looking one, but actually there is extra X. So this one we consider as external email. And then we can also use external reply by comparing the domain of from and reply to. Often targeted phishing attackers use a different domain for reply to. And also we collect size of recipients and the size of the carbon copy recipients as additional indicators. It is obvious that targeted phishing attacks will have only single recipient. However, many user business emails will have multiple recipients or carbon copy recipients. Next, we will have a look at the performance of our chatbot. Let's have a look at the performance of a chatbot. We used a data set of 10 million benign samples, and the data set also includes 350 phishing emails and 1,000 BC emails. We use time split to allocate 70% of samples as training and remaining 30% for test samples. We included two baseline models to compare chatbot. The first one is DistillBot, which has 6 transformer blocks. And another one is LSTM, long short-term memory. The model is a recurrent neural network architecture, which also used BOT's same embedding layer. We trained the 3 models on a GPU instance from AWS, and we assigned high sample weight for the BC samples and oversample minority class malicious samples to allocate balanced samples in each mini-batch. To compare performance, we use hours curves and area under curve. Also, we compare inference speed and the model size as key performance metrics. These hours curves compare our chatbot model with 2 baseline models. The top blue one is chatbot, and second one is DistillBot, and the bottom green one is LSTM. Our model outperformed the 2 baseline models. And our model achieved 0.8 true positive rate at 0.1% false positive rate. Next, we compare the performance when we remove adapters and the context input rated layers. The top one is chatbot, and the second orange one is when we removed adapters, and the bottom one is when context input was removed from the chatbot. We can see significant performance drop when we remove either adapter or context input, which demonstrate we can improve performance by using additional adapters and context-rated layers. Next, we compare the performance of 3 models with targeted BC samples. We assigned high sample weight for BC samples, and we achieved high performance for detecting those BC samples, and the chatbot outperformed the 2 baseline models. Next, we compare performance for phishing emails. We divide the phishing emails into 2 groups, English and non-English emails. Our chatbot outperformed for English and non-English emails, and our model was based on the multilingual bot, so we can see significant performance when we use the model for detecting non-English emails when it compares with simple LST model. Next, we compare the inference speed. DistillBot has 6 transformer blocks, and the chatbot has 3 transformer blocks. So we achieved 2 times speed up in inference time when we measure the performance on a CPU machine. As the number of blocks decrease, the inference time can be reduced. Next, model size. For comparison, we divide the model size into two parts, embedding and transformer blocks. DigitalBot has 6 transformers and has 92 million parameters for embedding and 42 million parameters for transformer blocks. And the catbot has 6 transformer blocks. We reuse the same embedding parameters, but we reduce the number of parameters for transformer blocks by 50%. In total, our model size is 85% of baseline model. When we apply the same mechanism for English version, the English catbot will have 71% of parameters from baseline model. Next, we will inspect how catbot generates outputs. We use a LIME method to interpret our predictions. LIME is a local interpretable model agnostic explanation method, which can be applied to any black box models. We can understand a model by perturbing the input and understanding how the predictions change. The first LIME example is for a benign email. The prediction score for this email is close to 0, and we highlight legitimate tokens with blue color and malicious ones as the orange one. And this one, we don't have any high weighted tokens for malicious ones. Next, we have a BC sample. The model prediction score for maliciousness is close to 1, and the model recognizes transfer and urgent payment as high-weighted tokens. Next, we have another BC sample, which is related with gift card. And the model prediction score is close to 1, and card and urgently. The tokens are high weighted for this email. Next, we have 2 handcrafted social engineering emails. They look quite different, but if you read the text carefully, they are asking the same wire transfer. And model predictions are close to 1 for both emails, and the highlight tokens are payment and swift or as soon as possible. These examples demonstrate our model's ability to understand complex text, and contextually similar emails can be identified. In conclusion, our catbot is a carefully re-architectured transform-based model. With this architecture, we achieve both high speed and high accuracy in detecting handcrafted social engineering email attacks. In the future, we want to apply the same design decisions to new GPT-3 model. Thank you. Do you have any questions?